Hi, it's Alan Edelman and Philip the Corgi, and this lecture is about structure. So to give the idea, let's talk about matrices. You all know about matrices. They're pretty simple objects. They're just n by n tables of numbers, right? Well, no, not exactly. Wrong. Well, maybe, right? So the surprise answer really is matrices are not necessarily m by n tables of numbers. Well, you can always think of them as m by n tables of numbers, but that doesn't mean you have to store m times n numbers on your computer to represent a matrix. So in this lecture, we'll talk about matrix structures and how we might save storage, often using far less than the m by n numbers that you might often think of as required to represent a matrix. So the bigger message here is take advantage of structure. Always take advantage of structure. In this lecture, we're going to take advantage of structure primarily for saving storage. But we can also take advantage of structure, and maybe we'll see this in future lectures, or you might see this in future classes. You can take advantage of structure to save time as well. In fact, most of the best algorithms and most of the best computational thinking is about taking advantage of the structure of a problem. So in Julia, it's often possible, we see this more often than you think, that the structure can be taken advantage of. And the good news about using Julia is there's no overhead to using structure. In fact, it's absolutely recommended. Other dynamic languages might incur some cost, but with Julia, it's absolutely perfectly reasonable and often done to represent the structure. Go ahead and do it. It is highly streamlined. So what am I talking about? Let me kind of give you the idea by starting with a vector that shows up in machine learning. It also shows up in linear algebra. In linear algebra, it might be called the column of the identity matrix. In machine learning, it's called the one-hot vector. And it's simply this. It's a vector that is all zeros except for one entry that's one. For example, this vector over here has length 6, and the second entry is a 1. The other entries are zeros. So the 1 is the one hot. The 1 is hot. The 0 is cold, you see. So this is a one hot vector of length 6 with the hot element being number 2. So if you look at this, you'll say, well, okay, there are 6 numbers here. There are 6 numbers here. But maybe I don't really need to store 6 numbers. Maybe I can just somehow store 2 numbers. And you'd be right if you thought about it that way. So you can have just the number 6, which is the length, and the number 2, which is the element that's hot. And somehow the number 6 and the number 2 should be able to represent that same object that in your mind is length 6. Okay, you don't need to store 6 numbers to have in your mind the abstraction of something that has length 6. And by the way, this is not about just deleting zeros. I mean, we could also talk about a one cold vector. So the corresponding notion is a vector that's all ones, except for one entry that's cold, right? And so again, you could represent one cold vectors, but with the numbers 6 and 2, if you have a context that it's one cold. So you don't have to store all those ones. You just need the 6 and the 2. You don't need any zeros or any ones, just the 6 and the 2 and context to say that this is a one cold vector. This is how we build a one hot object in Julia using just 2 numbers. So a Julia type is created with the word struct. It's going to be built from 2 numbers, n and k. That's all that's really going to be in there is the n and the k. And here there's a little bit of punctuation, this less than colon. What does that mean? Julia's full with all this kind of punctuation. This says that one hat is going to be a subtype of an abstract vector of integers. So in simple English, we want the one hat to pretend to be an ordinary vector, even though we're going to store it with a lot less information, wasting a whole lot less storage. So we're going to pretend that a one hot is a vector of integers, but in fact, it's going to be a one hot. Okay, so to create something that has the pretense, you actually need to only define 2 functions. We need to get the size of a one hot object. So the size will be the n field of the one-hot object, and it's put into a tuple of length 1, because size is always meant to be a tuple. And let's talk about what should happen when we type x of I. Well, when we type x of I, we should simply check whether we only have to check whether the hot element is equal to I. And so that's exactly what happens here, right? We just check if it equals I. Okay, and so if I were to create a one hot of 6, 2, as I do here, you could see that my one hot vector looks just like, it looks just as if I had typed 0, 1, 0, 0, 0, 0. Right? That's all you see. I can kind of make it vertical or horizontal, but either way, it is the one hot vector like this. Now, on the next cell, I do a dump of my one hot vector. This lets me see inside. And of course, you could see that the dump shows you that only the two numbers are being stored, 6 and 2. So don't let the printing fool you. Well, maybe it's meant to fool you. It's in your mind, you could think of it as a vector of length 6, right? You could think of it as the second column of the identity matrix of a 6 by 6 identity matrix. But in fact, it is just stored with the numbers 6 and 2. Okay, and it might be reasonable just to kind of show off, because we actually use this. Let's just show you that if I do take, here, I guess I'll do it here. If I do take my one hot vector of 3, it for sure gives you a 0. Why? Because it says, does 3 equal 2? The answer is false, and it turns the false into the integer 0. On the other hand, if I go on my one hot vector of 2, does 2 equal 2? Yes, true, and we get the 1. Okay. I kind of like to see these sorts of things both in vectorial and picture format. So I kind of like turning it into an image, so a bunch of colors really. So here you can see here. Let's play with this. As I slide the second slider, I want you to look both here. Let's move this up a little. I'd like you to look at this vector and as well as the vector of colors, and you can see it moving. I can make one hot vectors of various different sizes. Right here I am of size 7, and you can see all the 7 possibilities and so forth, just for fun. Okay, and I guess I don't need that. All right, so hopefully you now see the idea that a vector, or more generally a matrix, or even any array, you don't necessarily have to store it as a table to use it as a table. So let me show you a couple more examples so that to completely firm up the idea. And we're going to use this idea to sort of get the key information to be able to compress images at the end of this, towards the end of this lecture. So let's talk about diagonal matrices. Okay, so here's a 3 by 3 diagonal matrix. If you saw diagonal matrices in high school, you might have written it out with all the zeros. So here's a diagonal matrix. 5, 6, and minus 10 are on the diagonal. Okay, so there's your matrix M. But here, what I'm going to do is tell Julia that to convert it to a diagonal matrix, you could, of course, directly create a diagonal matrix in Julia, but I've created a general matrix, and I'm going to now store it as a diagonal. Maybe it's good to show you that you could have directly built a diagonal matrix with a syntax like this, and then, of course, you never would have wasted memory in the middle of this operation. Okay, but here you see this is a 3 by 3 diagonal matrix, and as you'd expect, the amount of storage is just 3 numbers, not the 9 numbers. And so, in fact, if you take a look, if I dump M, you see all 9 numbers are being stored. But if I dump diagonal of M, you could see that the basic information that's being stored are the 3 elements. Okay, so at the risk of repeating the main message, always look for structure where it exists. If it comes pre-built in Julia, like diagonal matrices, then use it. If this is a structure that's not already readily available in Julia, build it yourself. You don't have to ask for permission. That's another main message. Let's just go ahead and do it. I'm now going to talk about another commonly used representation for matrices, and that is the so-called sparse matrix representation, where we do not store any zeros in the matrix. So this could be a data matrix. Perhaps some of the entries are absent, so we think of it as zero and we don't want to store it. Or it could be a numerical matrix, which just happens to have a lot of zeros, and you don't feel like there's any great use for storing it. So there's the sparse representation, and there's going to be two versions of the sparse matrix representation that I'll talk about. One will be the ij value or ij aij representation, and I'll briefly touch on the so-called CSC, or column sparse compressed format, but I think I don't want to go into that too far. So first of all, here was this diagonal matrix M with the entries 5, 6, and -10. And here is a pretty obvious representation for the matrix. It has the row and column indices, the 1, 1, the 2, 2, and 3, 3, and the value, 5, 6, -10. So this is what I'm calling the ij aij, or the ij value representation. I'd like to briefly show you the CSC sparse format. It's not the only format, though it's a commonly used one. The CSC stands for column sparse compressed format. And I'll show it to you with this matrix with 0, 8, 9, 5, 0, 0, 12, 0, 4. So when you represent it as a sparse matrix, Julia's first choice is the CSC format. It's not the only format, but some people think that it's a good default choice. I think that's arguable as well. So here it is. If I dump it, the M and N are easy to understand. It's a 3 by 3 matrix. And let's see, let's go skip to the bottom. The non-zero values are, they go this way. They go by columns, hence the column format. 5, 12, 8, 9, 4, you see. So these are the numbers that are being stored, but there's a little bit of overhead because you have to also somehow say where these numbers are located. Well, let's see, the row index is easy to understand. This is in row 2, this is in row 3, this is in row 1, this is in row 1, and this is in row 3. So that's easy to understand. The column pointer takes a little bit more getting used to, but what's going on is it's going to say which entry starts with the column in which position. Let me give it by example. This 1 is going to point to the 5. Okay, this 3 is going to point to the 8. The 4 is going to point to the 4th element, or the 9, and the 6 is going to point after. The 6 is basically saying we are now at the end. So the 1 pointing to the 5 says the 5 is the first entry in the first column. The 3 pointing to the 8 says the 8 is the first entry in the second column, right? The 3 is the second number in the sequence. 4 is the third number in the sequence, so we count to 4 here, we get to 9, and 9 is the first entry in the third column, okay? And then finally, 6 says we're beyond the end, and so we go here and say it's beyond the end. There's no 4th column, okay? So that's kind of what it's signifying. So I think what's confusing, perhaps to some people, is that this 3 is in the second position here, which means that it's going to point to the second column, but it's going to take the third entry. The 4 is in the third position, so the 9 corresponds to the 4th column, right? I hope that makes sense. Okay. Let me kind of talk to another kind of way of compressing information, a little bit different from simply not storing numbers. This is more about like summarizing numbers, okay? And we could think a little bit about, here's a random vector of a million entries, okay? A vector will be good enough for this purpose. Here's a random vector with a million entries. The entries are just digits from 1 through 9. And you can ask yourself, what do you have to do to convey the important information to somebody else? What would you have to communicate? What would you have to store? Well, some people might think that since the numbers are random, you might have to store all the million numbers. Some of you might have heard of various ways of compressing the information in a lossless way. That means that you can store this. There are procedures, there are algorithms, for example, run length encoding, which will store the same information but with fewer than 1 million numbers. Okay, but let me go more extreme and talk about statistical information. So I'm just going to take the mean and the standard deviation, and just for fun, pointing out that because these are random numbers, I know the theoretical limiting mean is 5, and the square root of 20/3 is the standard deviation. But the main point is that sometimes, and again, it depends on context, the mean and the standard deviation is enough information from this vector, and you could throw away the 1 million numbers. Now you might say, some people might say, throw away 1 million numbers, well, I might need it someday. Well, those are the sorts of people that probably have too much clutter in their basement. You may need it, you may not need it. It's up to you. It requires judgment, good judgment, as to whether you need to store the information or if you just need to store the summary. Okay, and just a little bit of Julia, in case you don't know what a mean is. I guess everybody knows it's the sum divided by the length, and the variance is the difference of the data from the mean squared divided by the length minus 1. The length minus 1 always sort of confuses people, but there's a simple explanation for it. But the funny thing is, it doesn't even matter very often, because as long as your data is, not of length 1, 2, or 3, it probably doesn't matter too much. Maybe, if it's up, 50 or more, I don't think it matters. Here, the standard deviation by definition is the square root of the variance, and so just to show you that we got the same number here that was built in with Julia. But what I want to do now is move into another kind of compression, a kind of image compression, but I'm going to do it with numerical examples. And I'm going to start with something that I think you saw in 3rd grade, maybe in 2nd grade, maybe 4th grade. I think you saw it in 3rd grade. I saw it in 3rd grade. Multiplication tables. Okay, so here, I hope you all recognize this. Maybe it brings back memories. Here's the 10 by 10 multiplication table. Okay, it is simply, I take every number I in the ith row and j in the jth column, and I multiply I times j, and that will give me the multiplication table. While I'm at it, let me define an outer product. This is a linear algebra term, but let's just call the outer product, where I can take x times y for x in v. And I'm going to change this to, I like this sort of math notation. Hope you like it too. It's the same as in. But for every x in v and every y in w, let's just do the multiply. This would allow us to get general multiplication tables. So for example, what this lets me do is I can make a little 3 by 3 multiplication table, or I can go as far as maybe a 12 by 12 or even further. So our co-professor, Dave Sanders, tells me that it's required in Great Britain not to stop at 10 by 10, but 12 by 12 is the one that everybody uses in Great Britain. So here's the 12 by 12 multiplication table. Okay. Here's another outer product, 246 with 10, 100,000, just to show you an example of a generalized multiplication table. So you see that in the first row, we have 2 times 10, 2 times 100, 2 times 1,000, right? Or 4 times 10, 400,000 in the second row, and so on. Okay. So if you asked how much information there is in the regular multiplication table, well, I think you could see that you could store, let's make it 10 by 10. You can store all 100 numbers, but you also, if you have context, all you need is really one number, right? The one number 10, right? Or the one number 11, and then you just need some context on how to compute it, right? So I don't need, like if I asked you right now, okay, if I have the billion by billion multiplication table, and I asked you for the entry that's in the 5, 7 position, you could on the fly tell me it's 35, right? You didn't store all those numbers and look for it, right? You just know that the 5, 7 entry is 35. You can compute what you need when you need it, right? So, you can compute it just when you need it, right? And that's kind of what the point is. You just need to know the number k, right? And then when you pick out an index, an element, you just need to know the indices, okay? Here is a bit more, here's another outer product, a multiplication table, if you will, where I suppose it would be a little harder to see the structure, though you might start to notice it if you get good at it. For example, I would say that this number is just about half this number when I look at it. So this is about half, this is about half. Oh yes, I see. This number is just a little more than the first number. Yep, this one's a little more than the one in the top of its column. Okay, yeah, I'm starting to see it. Okay, or here, if you like, you could see a picture of the outer product of, in this case, of a 10 by 10. And you start to often get these sort of striped or maybe plaid pictures. It's not unusual to sort of see these plaid pictures when you kind of show the, from an image point of view. So image is, from 0 to 1, uses the colors of the rainbow. But you do get to get these sort of plaid pictures. So can we go the other way? If somebody gives me one of these generalized multiplication tables, like the array here, can I go the other way and get two matrices whose outer product will be what I need? Okay, and the answer is you can, and here's a little function that does it. I mean, the basic math is in 3 lines. It's very simple, really. If the multiplication table, you take the first column of your table, call it V, you take the first row of your table, call it W, and most of the time you could just take W divided by V of 1, and that'll give the right answer. If you can't divide by 0, and if it was a 0, it would be all zeros anyway, so you can just do a check for that. And I think it just seems like a good idea to check if you actually get something that's approximately equal to your table. Otherwise, you could tell the user that the input is not a multiplication table. And so here, for example, I factored the outer product of 1, 2, 3, 2, 2, 2. And of course, I got 2, 4, 6, 1, 1, 1, just showing that there's kind of an arbitrary scaling. I mean, I could always multiply this by 17 and divide this by 17, and I would get the same outer product. And so there's a kind of choice to be made, right? You might think about the fact that any multiplication table then could be represented, you might think it could be represented by m plus n numbers, but in fact, m plus n minus 1 are sufficient. Okay, here's an example where I try to factor a 2 by 2 matrix. It's not a multiplication table, and my little error message kicked in and said input is not a multiplication table, just as desired, just as expected. Okay, so a multiplication table can be factored and stored, or possibly never even built, right? You could just store the factors, and that could be good enough. And again, if I have my V and W, and I just want to calculate the IJ entry, the moment I need it, I can compute VI times WJ. Now, what can we do with multiplication tables? Well, we can add them, right? So here's a sum of 2 3 by 3 multiplication tables, right? So if I went from 1 to 1, this would be a single multiplication table. This is the sum of 2 multiplication tables. Here's the sum of 3. Okay, so let's just stop with 2. And now here's the question. Can I actually find the structure? Can I find out that this was made up of 2 multiplication tables? Well, interestingly enough, there is a kind of fancy linear algebra decomposition which will do this for you. Okay, and my goal right now is not to talk about how you can calculate this thing by hand. I don't want to even explain the linear algebra. You might see it in a linear algebra class. I just want to mention it. It's something called the singular value decomposition, and it is really good at finding the multiplication tables that need to be summed to form a matrix. And the great thing about the singular value decomposition is you can choose to throw away as many multiplication tables as you like. Just keep the first few, and this will be a good approximation to a matrix. So here is the SVD of the matrix. The SVD of the matrix, the singular value decomposition, always returns a matrix, a vector, and a matrix, right? So let me put that in here. So U and V are matrices, okay, and sigma is a vector. Okay, they have some special properties. Again, you might learn about them in linear algebra. Many people like to connect singular value decomposition to eigenvalues. It's not my favorite approach, though it's kind of, it's a simple thing to do because eigenvalues appear in every linear algebra class, so you could kind of sort of dump them in afterwards. I think that's backwards. I think the SVD deserves its own life, and people get a little too caught up in calculating by hand. I think that's not even necessary anymore. But again, that's a bit of an editorial that maybe we don't need right now. So let me just sort of show you, I'm going to just show you how to use the SVD for the purposes of this computational thinking class. But it would be great for you to learn more about the SVD. So many things you can learn. But here I'm going to do, all I'm going to do is calculate the U sigma and V. And then I'm just going to take two outer products. I'm going to take the first column of U, and then I'm also going to take the second column of U as the first argument to my outer product. And I'm going to take the scaled, sigma is going to tell me how to scale it, a scaled first column of V and a scaled second column of V. And I'm going to add them up. And I'm going to notice that this is somewhat approximately this matrix. Okay, it actually gets better for bigger matrices with structure. But here I'll kind of take a few different cases. You could see that here's a 3 by 3 matrix. Here I'm adding two outer products. And you can see that this is not a bad approximation. Okay, so it approximates very well. I could add more. For example, if you want the exact reconstruction of the matrix, I would copy this and I would put the 3 in. Of course, I could make this more general and put a sum, but maybe it's good to just see it, right? So if I put this in, you'll see I reproduce the matrix entirely, but I could leave out pieces, right? If I leave it out, again, it serves as an approximation. So let's continue with this. Let's see what we can use our SVD for, our singular value decomposition. Well, here's a flag, okay? My flag here is an outer product where it's made up of just ones and twos. Okay, so here it's an outer product. It almost looks already like a flag numerically. If I use these distinguishable colors, I think this makes it even look more like a flag. I'm just indexing into distinguishable colors to make it kind of visually pretty. Okay, so this is one outer product, just stripes. Okay, here I'm going to take two outer products. Just to make it easy, I'm taking the flag plus the flag transpose, which means that I've taken the flag plus the flag transpose is really nothing other than, and I guess I could, it's nothing other than taking the outer product one way and then switching the arguments, which I guess I could almost cheat because there aren't that many entries that are different than the arguments by just changing the middle arguments, you see. Okay, so here's the actual, here's the actual matrix, and of course, if I take CS of this by indexing into my colors, I get this picture. All right, so we might explore this in the homework, that lots and lots of flags can be written as the sum of outer products. Okay, thereby saving, I mean, already you could see, I mean, you might be able to imagine doing better than this, but I'm not using 81 numbers by any means to represent this flag. Okay, well, now let's kind of push this all the way and talk about actual real images. Okay, and so here what we're going to do is we're going to download an image of a tree. Okay, so there's a tree, and we'll downsample it a little bit for just to make it so you can see it, right? And so in Julia, in the image processing, there's something called the channel view, which basically takes every pixel and turns it into its red and green and blue components. So that by the time you're done, if you turn it into floats, which makes it all the red, green, and blues between 0 and 1, we're going to get a three-dimensional array that's 3 by 216 by 384. So what's going on here is the vertical size in pixels of this picture is 216. The horizontal size is 384, and the 3 represents the 3 channels, the red, the green, and the blue. Okay, we could actually separate out and get matrices, two-dimensional matrices, by using the each slice command in Julia. We're going to slice it along the first dimension, the dimension of size 3, and this will give me the red part of the picture, the green part of the picture, the blue part of the picture, which I can reconstruct and put next to each other, and you could see it. I kind of like the use of the tree because you can see very closely that the tree is basically green. The green shows up in the green part, and it kind of looks just like a shadow through the red filter or the blue filter. It's much blacker. It really is a shadow. Okay, but anyway, there's the three channels, the red, green, and blue pieces of the tree picture. Okay, and what I would like to do is break up this picture using the SVD. So I'm going to take the SVD of the red part, the green part, and the blue part. Remember, the U and the V are matrices, the sigma are the scale factors, they're the vectors. And let's take a look at what happens if we try to approximate our tree with one multiplication table. Well, there you see the plat picture. Maybe it's as expected. I mean, the tree kind of sort of smeared to the left and right. The trunk kind of went up and down. You could kind of see the ground is sort of being spread to the right. It's pretty much, I think, what you'd expect. Okay, now let's kind of move one over, and now we have the sum of two addition tables, right? I'm basically reconstructing this, and I'm summing this, and I'm taking up to 2. So this looks like, maybe, can I call this like a Minecraft tree? It's going to have that rectangular shape now. With 2, you can somehow get, the tree can sort of become blocked. The ground is a bit more clear. The trunk is still kind of influencing itself all entirely vertically, but we can kind of continue and go to 3, and now the tree can at least have a bit of staggering now, kind of it's stepped, and we can go a little further. Here's the sum of 4 multiplication tables, and so forth. So we can keep doing this. After a while, you can recognize it clearly as a tree, but it has some ugly artifacts. And we could keep going a little bit more. Remember, this tree was, what did I say the size was? I mentioned it before. It was 216 by 384, but probably here, 60. I guess I don't completely love those artifacts, but pretty closely, you're getting a pretty decent tree. Some pictures work better than others, and depending on what visual quality you like, but it does show you that the singular value decomposition is a way of extracting the structure from an image. It's not the only way. A lot of image compression schemes like JPEG, they use something different entirely that's probably more effective in practice for images. But the SVD is certainly quick and easy and dirty that you can use. It's very easy to use, and it is used to compress many, many things these days. So just to kind of sum it up, in lots of times these days, you have all kinds of data. And if the data could live in sort of a high dimensional space, but it lives on sort of the analogy of a plane, it's called a hyperplane, then the SVD does a very good job at compressing the information to the important pieces. This is the idea behind something you may see in statistics called principal components analysis. And it also is it gets generalized into machine learning, where you pick out the small number of parameters.